Hello, dear friends, my dear professor, and dear classmates. I am ARMv7, a junior computer science student at EDU University. Today, we'll discuss an interesting task question from computer organization and architecture. So, this is the instructions of assignment. So, we are required to create a loop in assembly without using branching. All right, we have to only use move PC some value. And this loop, what's the purpose of this loop? The purpose of this loop is finding sum of numbers from m to n. Imagine m is 1 and n is 4. We have to find the sum of all numbers from 1 to 4. And here we'll use some registers and they are clarified here. So R0 will be used for M, R1 will be used for N, and R2 will be our sum register. Then R3 for storing the bytes per word value. So word value, it depends on actually architecture of computer. In 32 bits or computer architecture, it's 4 bytes. But in 64 bits computer architecture, it's 8 bytes. But in our simulation, which is simulator here in our ARMv7, so here it will be 32 bits architecture. So it will be 4 bytes, let's say. And use R4 for storing the computed offset, computed distance. So we'll talk about it. Then R5 for computed actual address to branch those. And we have a supervisor called 2 to stop our program. So, all right, I hope we can start. Okay, this is our source code. Of course, we'll deduce and analyze this code line by line, and we'll discuss interesting points here. So, let's start with the first line. We have move R6 PC. So, what's PC? Let's clarify these. PC, well, let me write it here. So PC is program counter, all right? It's a special type of register that hold um, the address of instruction, okay? It holds the address of instruction. Okay, and here what will happen? R6, we are, let's say, passing the value of PC, which is address of instruction, to R6, register 6, all right? And by the way, let's compile and load and see what happens here. Okay, all registers are 00, step into one step ahead. Now we see R6 is 8. Okay, 8, it means this, all right? 00, 04, and 08. So this. Interesting point. Actually, this is a key point here. As you see here, the value of program counter is 008, not 000, not first, let's say, row, but the third row, 2 row ahead, or 8 bytes ahead. That's an interesting point. What's the reason? Why it's not 000, but instead it's 008? It's because of ARM's pipeline architecture. So we have ARM pipeline architecture. All right. So what's ARM's pipeline architecture? So we know that how let's say does CPU work. So it fetch instructions and then decode and execute. So why did I write them separate, like fetching and then decoding, executing in the same column? It's because these are two different stages: fetching stage and decoding, executing. So to increase performance, architects invented this pipeline architecture. And what is the purpose of this pipeline architecture? We are fetching two instructions ahead and then decoding and executing them. All right. And we said the program counter is shows address of instructions. So since we fetch two instructions beforehand, which are these, so PC will refer to the next instruction address, which is this. All right. And if we look at here, the address of this instruction, as you see, this one, I couldn't, let's say, highlight it here. Okay, I did. Maybe I do go backward. Okay, oh, good. Here, as you see in yellow line, the address is 8. I hope I explained myself and this point here. All right. So PC here, by the way, what did we do? PC, we moved value of PC, which is address of instruction or 8-byte ahead instruction. All right. We move value of PC to what? To 6's register, to R6. All right. Now let's continue. Here, what do we do? Let's say we initialize R0 to 1, and then we initialize R1 to 4, and then we initialize our sum register, which is R2 to 0, we initialize it, and then what do we do? R3, okay, R3 was uh, bytes per word value. Although we don't use it here, I don't need, to be honest, to use it here. But due to instruction, just I demonstrated it here. Okay, I displayed it here. But even I have better solution, by the way. I have better solutions. These I will demonstrate it. But to follow this, let's say, instructions, just I solved it like that. So let's continue with the next line. And sum is subtraction. What do we subtract? We subtract program counter current value and register 6, which is it is initial value, let's say, right? And here we find offset. All right, offset uh, between here and the initial value, and that offset is R4. All right, we store that value in R4. Let's say in R4. Okay, so good. Now, next move, next row. Here we add. What do we add? We're taking this value and adding it R4. So the address of initial address of counter and this R4, which is this, and store it in via R5. By the way, you can ask this question: why did we subtract it here? Why not in other place? Why not here? Why not here? All right. Why did we did we subtract it exactly here? That would be a good question. It's because I did it intentionally. Why? I know that program counter refers to the address 8 bytes ahead. So 4 byte, 8 byte. It refers to here. So here in ninth line, program counter refers to 11th line, let's say, like this. All right, the address of this instruction. Okay, it refers to here. And I will need uh, the address of this instruction. I will explain why in a few minutes later, but I will need the address of this instruction. So therefore, I did it exactly here. I found offset value and then added that offset value to the what initial value of PC and keep it in R5. That after I will use R5 to access here. All right. So we know what is this, and now let's start with the next instruction. This is compare, and this compare will compare the R0 and R1. If R0, so generally it's subtract R0, it's subtract R1 from R0. So if R0 is greater, in that case, it will be positive. If less than, it will be negative, or if they're equal, it will be zero. So, okay, this will compare these registers, the value of those registers. In initial case, it's 1 and 4. I initialize them like this. So, this is a supervisor call. Supervisor call greater than. If R0 is greater than R1, it will stop. Okay? Okay, let's continue. Add LE, add less than or equal to. This means this. All right? Add less than equal to. So this instruction will be executed if R0 is less than R1 or equal to R1. All right? In this case, it will be executed. And what will be done here, let's say, it will add R0 to R2 and keep it in R2. All right? R2 is sum. All right? So it would be better to show, to compare it with for loop, like maybe I can show it here. See online compiler. So we can write some loop here, right? For int is 0 is less than, let's say, 4. Or let's start is with 1 to make it similar our example. 4 into then sum is equal to what? E, isn't it? And here we'll initialize in sum 0, right? So what do? We are adding, which means sum is equal to sum plus E, right? We'll equalize sum plus I, all right? Here it will be 0 plus 1, then it will be 1 plus 2, which is 3, then 3 plus 3, 6, 6 plus 4, 10, all right? We apply the same logic here. So R2 here, R2 is equivalent to sum. So R0 is equivalent to E, right? So yes, that's it. And next operation, which is E++ operation here. I mean, adding 1 to E, you can write R0 is equal to R0 plus 1, right? But this will be executed only if R0 is less than or equal to R1. All right, keeping your mind. And we have the last point here, which is moving R5 to current program counter. What was R5? The address of this instruction. So here we create loop. Perfect. Now, program counter will refer to this address. And again, it will start here. Come here, come here, come here, again, again, till R0 will be bigger than R1. So let's compile and load. As you see here, it was here, step into here, 1. So R3, 4. As you see. So look at here. So R4 is, what was R4 by the way? R4 was offset value, right? Offset value is 14 here. Then compare R0, R1, here 1, 4. By the way, it's not 14, it is 20. These values are hexadecimal, guys. Keeping your mind. I'm sorry. These are, I did some changes. I don't know what happened here. Okay, let me reload this page. Okay, let's compile and load. Let's start from scratch. So R6 is 8. It shows the address of this instruction. All right, perfect. Step into, and then R1 is 4, R0 is 1. Okay, R0 is 1 as you see it. Then this will be executed, and you see it changed. It's 4. The value of R1 is 4. Then R0 is 0, same. Then R3 is 4. You see change here, change here. Then then you see R4 is the difference between PC and R6, which is here it will be 20. This is hexadecimal. All right, 4 plus 16 is 40. 20, I'm sorry, 20. So it's 20 bytes. Indeed, it's 25. The 20, I am sorry. I'm sorry. Indeed it's 20. Why? 1, 2, okay, 1, 2, 3, 4, 5. 5 times 4, it's 20. All right. So let's continue. And we'll add R4, R6, R5. So we'll keep the address of this. All right. You see, R5 is the same as this address here, which is the address of compare instruction. Perfect. We did it correctly. Now, let's step into. So it will not stop since R0 is not greater than R1. R0 is 1, you see here, and R1 is 4. So it will not stop. It will pass next. Here R0 plus R2. So R2 will be 1. You see it change? Then we will move Okay, now the second loop starts. As you see, it came here and it will continue. You see, R2 is changed, it's 3. Now it's 6. Now it's 10. It's hexadecimal, guys. So it's 10. So compare. R0 is 5, R1 is 4. So it's greater. As you see, it will not go downward, it will go upward. See? It's because program stopped and started again. So that's it. By the way, I have better solution. I said that I have better solution. Now let me demonstrate that solution. Initially, let's start from scratch. What will I do? I will not use this. I make it as comment. I don't need this. Even I don't need this offset. Why? I will tell you. I will tell you. Here I know the so let's do something like that. Let's change this. Uh, Even I will make this as comment. Okay, what will I do? Uh, so two ahead. So from here, I will add a move R5 PC. All right. So I know that here PC refers to here, 8 bytes ahead, right? Four. So 4, 8 plus 8 bytes in the next instruction. So it will be here. And it will be here or just a minute. Maybe I confuse something. Just a second. So what? No, I confused. So it will be, it will not be here. It will be here. All right. So it will refers to compare for 8 bytes. Okay, perfect. 8 bytes ahead. So even I don't need this initial. Press 6. I don't need this. I only need this. Okay. So it will work exactly. Let's try and see whether it works or not. Compile succeeded. See, let's see. Addle. And you see, again, loop started. 3. R2 is 3. R2 will be 6. Now, R2 will be 10. Perfect. Now it came here, CVS, and it will stop. You see, it stopped. So that's it. We get rid of a lot of code here. We don't need this. So we don't need this. Let me remove this. So we don't need this. Okay, we shortened, optimize our solution. It's better. All right. So that's it. Thank you for watching. I hope I, at least I tried to explain it in details. I hope it was clear for all of you. Thank you.